Okay, so let us do this sample problem about the isentropic efficiency of a nozzle. So here we have our nozzle, and you see that at the entrance of the nozzle, the pressure is 140, temperature 600, and a velocity of 100 feet per second. So what's going to happen through the nozzle? So obviously the pressure is going to go down, so the temperature will go down. But if the pressure and the temperature goes down, something must go up, and probably will be the velocity. So probably here we're going to have that V2 is going to be higher than V1. This will be the mass flow coming in, mass flow coming out. Okay? And if we do the diagram over here, the HS diagram, they say in the problem statement that we have steam, but again we can check that with the tables. So it will be here and here, so this will be P1, this will be P2, T2, P1, T1. So if we do the isentropic, let's say it will be here, flow line of S1 equal S2, so this will be 1, this will be 2S, and the actual process, what happened? We waste energy, so the entropy goes up. So let's say we'll go somewhere over here. Again, why is this figure important? Is because you see that the difference between H1 and H2S is larger than H1 over H2. Okay? So basically we know that then the definition for the efficiency of the nozzle, which is related to the kinetic energy, will be equal to what? Kinetic energy actual divided by the kinetic energy isentropic, we should give you V2 squared over 2 over V2S squared over 2. Okay? Okay, I'm going to try to put on the figure. So basically that distance over here this will be V2S squared over 2, and that distance over here will be V2 squared over 2. Alright. So the other equation we need, that I said before, is that if this is our control volume, and we write down the first principle of thermodynamics for this control volume, what do we have? So it will be Q dot minus power plus M H1 plus 1/2 M V1 squared will be equal to M H2 plus 1/2 M V2 squared over 2. So this is neglecting potential energy. Then we can see there is no any heat transfer in this problem. There is no power, so we can cancel out all the mass flows. So we have H1 plus V1 squared over 2 should be equal to H2 plus V2 squared over 2. So basically here we have the two equations that we derived, that we indicated on the previous video for the isentropic efficiency of a nozzle. So these are the two equations we can have to deal with, 1 and 2. Alright, so let's see what we need. We're going to need H1, H2, V1, V2. So V1 is given. We can find H1 from where? P and T, we know two things. We can go to the table and find H1. We can find H2. We know two things here, P2 and T2. Then, in order to find H2S, we use a condition that S1 equal to S2. Alright, so let's go first to find H1. Let me zoom out a little bit now. So to find H1, you will see from the table that state 1 is superheated. So that means we need to go to table A6E for the English units and add what? We need to know two things. So we know that P1 is equal to what? 140 psi, and that T1 is equal to 600 degrees Fahrenheit. So if we go to the tables, for 140 psi is this table over here, and at 600 we go over here. What is the enthalpy equal to? 1326.6, and the entropy to 1.7195. So let's see, we can write down H1 is equal to, let me not get lost, 1326.6, and S1 is equal to 1.7195. Okay, so we can do exactly the same thing for H2. This time, what do we know for H2? We know that P2 is 40 and T2 is 350. So let me zoom out a little bit and then zoom in for the table. So table A6E at P2 equal to 40 psi and T2 equal to 350 degree Fahrenheit. We need to find, in this case, just H2. So if we go to the tables, so for 40, let me zoom in over here. Let's see if the image gets more clear. Okay, basically you can maybe see that it's not really 350, there's just 320 and 360. So we need to look at the values for H and really S for the second part. So for 320, we have H equal to T equal 320, H equal to 1197.1, and S1 equal 1.7128. And at 360, we have H equal to 1216.9 and S equal to 1.7376. So let us write it down, because we probably have to interpolate over here. So for T equal 320, T equal 360, we have H, let's say this would be H sub A would be equal to 1197.1, and S sub A, let's call it that way, would be 1.7128, H sub B 1216.9, and S sub B is 1.7376. So we see that we need to interpolate for H2. So the first interpolation, if you want to do a little sketch over here, we need to find H2, and we know the temperatures. So we are going higher. So this would be, let's say this is TA, TB. So we have TA, TB, HA, HB, and we're trying to find the temperature here at T2, which is the 350, so we need to find H2. So that H2 from that figure is equal to what? HA plus, then we do the slope of the line, HP minus HA, TP minus TA, and that spacing on here would be the 350 minus TA. So if we substitute, that would be equal to what? 1197.1 plus 1216.9 minus 1197.1 divided by 360 minus 320 times 350 minus 320, and that is going to give us a value for H2 equal to 1211.95. So if I put it right here, this will be 1211.95, and this should be units watt, BTUs. Let me zoom out for a second. BTUs LB. Alright, so we have this one. Let's do this. And let's see if I find my other page. So this is H2, and we know H1 is over here. BTU LB. So now we need to find H2S. So in order to find H2S, what do? Remember, we use the condition of isentropic, which would be like the ideal case. So S1 equal S2. So in that case, we need to know two things. So we know S2 equal S1, and this is equal to what? From above, 1.7195. So that means now that we can interpolate, okay, the same thing we did over here, but this time we'll have H over here, but we'll have S over here. So let's see if I do the figure. This will be S sub B, this will be S sub A, this will be H sub A, this will be H sub B, and here we know the value of S2, so we can find H2S. Okay, so if I write down the expression for H2S, following exactly the same case as over here, we have H2S equal to HA plus HB minus HA, but this time we don't have the temperatures but the entropies, and this will be S2 minus S sub A. Alright, so if I substitute for the values, what are we going to have? We're going to have 1197.1 plus 1216.9 minus 1197.1 divided by 1.7. Oops, okay, 1.73. I forgot to write down something up, but I'm gonna do it now. 7376 minus 1.7195 times 1.7195 minus 1.7128. Sorry, this is 1.7128 over here. Because from this figure here, I give you H2, but S2 over here from the table is equal to 1.7376. Okay? Sorry for that little confusion. But if you do this calculation here, you will find that H2S is equal to 1202.45 BTUs LB. Alright. Okay, so let's go back to our first page and see what else we need to find. So now we know H1, we know H2 and H2S, we know V1 is given to us. We need to find what is the velocity at 2 for the two cases. For the actual case, when we go through this line, what will be the velocity at the exit, and what should be the velocity at the exit in the ideal case when we assume that it is isentropic. Alright, so let's do that. So, and in order to do that, we need to use the equation over here. So recalling equation 2, which is what? H1 plus V1 squared over 2 equal to H2 plus V2 squared over 2. So from that equation, we can find out that V2 squared over 2 will actually be equal to what? H1 minus H2 plus V1 squared over 2. So if we do the numerical application for that equation, what do we get? V2 squared over 2 will be equal to H1, which is equal to what? H1 is equal to 1326.6. Okay, in this case, minus H2, which is what? 1211.95. 1211.95. Now plus V1, but we're going to have to be careful with the units, plus 100 foot second square, and this is over 2, so 1/2. But remember, the units of this side will be BTUs LB, and here we have foot second square. So what we need to do over here is actually what? So maybe I should have done that differently. It would be 1 over 32.2 LB foot second square. This will be 1 LBF. And then we also know that 1 divided by 778 foot LBF is basically 1 BTU. So if you do this calculation, you're going to find that V2 over 2 squared to be equal to 114.85 BTUs LB. Okay, so similarly, looking at that equation, what can we do? We can find that. So similarly, you can find that V2S2 over 2 will be equal to what? H1 minus this time H2S instead of H2 plus V1 squared over 2. So that if we do the numerical application, what do we get? V2S squared over 2 So this will be the same. H1 is 1326.6, but this time H2S we found to be equal to, it's right here, 1202.45. And now we get to the same problem over here, so 1/2 100 foot/second square. And we're going to have exactly the same thing over here. Maybe I can write it a little bit shorter this time. It would be 1/32.2 lb foot/second square divided by 1 lbf, and then 778 foot lbf would be 1 BTU. And this is going to give us that V2 isentropic square over 2 to be equal to 124.35 BTUs LB. Alright, so basically now we are done, because in order to find the efficiency, what is the relation we had? Is the actual V2 square over 2 divided by the isentropic V2 square over 2. So finally, we're going to have the efficiency of the nozzle to be equal to what? We just look at it, will be V2 square over 2 divided by V2S square over 2, which that would be 114.85 divided by 124.35, and that is equal to 0.924. So basically the efficiency of the nozzle here is 92.4%. Alright, so this will be the end of this problem. So thank you for your attention.